We will now start today's CITA seminar, and we're very happy to have Kenta Hotokezaka here from Princeton University, where he recently moved from the CCA in New York. Kenta's an expert on nearly everything, compact object related by now, and through mostly coincidence, I think, he will discuss some of the implications of the binary neutron star merger that was announced this morning as well as some random experiments. Thank you.
Thank you very much. So today I will talk about the hottest topic today, which is neutron star merger reported LIGO today. So probably I don't have much time to discuss about the spin of binary black hole. Probably I mostly focus on EM counterpart of gravitational wave merger event. So by the way, I'm involved in this collaboration for the follow-up program of neutron star mergers. So this is outline. So I'm not observer. So what I'm working on is theoretical interpretation of EM signals, which is associated with the gravitational wave 700817. And there are many papers published today. So, but I will focus on these three papers. This one is focused on mostly optical and IR emission, and try to interpret all the data in multi-wavelengths. And also there is a radio paper, radio detection paper, and also the X-ray and UV paper. So let me begin with this historical paper. This is a prediction of what we should see in neutron star merger in 1989. So this paper discusses nucleosynthesis and neutrino and the gamma ray burst from neutron star merger. So they say in abstract, you can see the neutron star merger should be some burst of a gravitational wave signal. And also they discuss synthesized neutron-rich heavy nuclei. And also it is proposed as a site of the gamma ray burst. And remarkably, they also predicted that the event rate should be 10 events per year within 100 megaparsec. And this is kind of all confirmed, mostly confirmed in this year. So it is amazing. This was predicted 30 years ago. And so now I want to show you the animation of neutron star merger simulation. So this is the density profile of the neutron star merger in numerical relativity simulation. And this is a gravitational wave signal that emitted by this in spiral. So now two neutron stars are approaching, and then amplitude and frequency become larger in time. So now two neutrons are merged, and still, in this case, there is some object after the merger. So the gravitational waves are continuously emitted, and at some point, this object will collapse to a black hole. Then the gravitational wave amplitude also disappear at that moment. And you can see some material is around this central object. So if you look at this simulation on the more larger scale, so you can see some mass ejection from the merger. So this is 300 kilometer. This is about 3,000 kilometers. So you can see some material is ejected from the system. And in our simulation, we found like 10 to the minus 3 to 10 to the minus 2 solar mass with a speed of 0.1 c to 0.3. And this is basically driven by gravity and gravitational torque, and also hydrodynamical interaction of the neutron star mergers. So this outflow should produce some observable EM signal. And this is one plot from this paper. This plot, the predicted amount of ejecta from neutron star merger. So this axis shows the expected dynamical ejecta. So dynamical ejecta is just ejected this at the merger. And also there should be some disk wind from the remnant object. So this is expected disk wind outflow, the amount of disk wind outflow. So, and here's the total mass of the ejecta. This is 10 to the minus 2 solar mass, and this is 0.1 solar mass. So basically we expect this order of magnitude is 1% to 10% of the solar mass should be ejected from this system. So this is now some schematic picture what kind of signal we should see. So here we are here, for example. So this is after the neutron star merger, we have some black hole or some remnant neutron star at the center. And like as we see, there should be some ejecta around the neutron star, around the central object. And central object may launch relativistic jet. And if probably this relativistic jet produce some short gamma ray burst, and which can be seen if you are in this jet cone, because this is relativistically beaming. And this ejecta also produce some radioactive heated transient, which called Kilonova or Macronova. So here we call it Macronova. And also this ejecta in the end interact with the ISM, which produce synchrotron radiation, and we may see some afterglow in wide wavelength range. So, and this is a light curve that we expected. So this is basically written in 2013. So in optimistic case, we may see short gamma ray burst. This is time scale. This is short gamma ray burst 0.1 to 1 second. And then some short gamma ray bursts have some extended X-ray emission and also X-ray afterglow. And here is optical afterglow. So this is a light curve of the optical afterglow. And this is some optimistic case. But these are probably beamed. However, we should see some isotropic emission, for example, optically. In optical, we should see Macronova, Kilonova, and the radio afterglow and the radio flare. This is radio remnant of the neutron star merger ejecta, should be isotropic. So people expected this kind of picture. So then what we saw in this gravitational wave event was something like this. This is not really different from this. So surprisingly, we saw some short GRB, but which was very weak. And also we see some X-ray on this time scale. We didn't see these early time X-rays, but we saw the X-ray afterglow at the 9 days after the merger. And also Macronova was quite bright compared to the expected. So this was expected, but now we see brighter signal.
Also, the short GRB was not 10 to the minus 2, 10 to the minus 1 seconds.
Oh yeah, it was
delayed by a second.
Right. So yeah, so it should be here. Yes, thank you. And we also see some radio signal. And still, we are not really sure what is the origin of the radio afterglow. Probably relativistic jet, probably non-relativistic ejecta. So this is a localization by LIGO and Vargo. So here is the localization area of the gravitational wave. And integral and Fermi satellite, they see gamma rays from this area. So which are these areas coincide the localization area of the gravitational wave detectors. And optical telescopes and optical follow-up identify the host galaxy, identify the optical signal, and identify the host galaxy here. This is the host galaxy. This is the name is this. This is one of the S0 type galaxies at the 40 megaparsec. And this is a host galaxy. And this is the optical, it's near infrared signal actually. So this is the location of this transient that we see. So this is so here I summarize some timeline. So we see gravitational wave detection, and after 2 seconds after the gravitational wave, after 2 seconds after the merger, the gamma ray, we saw the gamma rays. And then we didn't see X-ray, and then we saw UV signal and optical signal at half a day after the merger. And after 9 days, we see X-ray, and after more or less 2 weeks after the merger, we saw radio. Okay. So now I'm going over these, what is the detections and what is the interpretation of this detection. So here's optical. So this is the bolometric light curve of optical UV and infrared. So this is time and this is luminosity. So these are the detection measurement. So basically what you see is within 1 day, so we didn't see really rise. We just see the peak point here, and then it declines. And the peak luminosity was 10 to 42 erg per second, which is actually brighter than the expected. We expect something like 10 to the 40, less than 10 to 41 erg per second, but actually the signal was here. And also, so this decline is basically consistent with the our process radioactive heating rate. So we can calculate what is the heating rate, how heating rate behaves as a function of time. So which is heating rate should be t to the minus 1.3 or something like this. And actually this curve is more or less consistent with this heating rate, and a little bit faster because some gamma rays escape from this without give heat to the ejecta. So basically this bolometric light curve is consistent with the radioactive heating rate. And from this comparison with how much heat we have and what is observed luminosity, we can estimate how much our process element we need to reproduce this kind of light curve. So for example, this is, for example, theoretical light curve we calculate. So in this calculation, we put like 0.05 solar mass, but in order to explain this light curve, we can get we need at least 0.02 solar mass of the radioactive material to explain this light curve.
And do you need faster expansion than the previous model suggested?
Yes, actually, it's actually consistent. So this is a photosphere, and this is a velocity. So v over c as a function of time. Can you see it? Here is 0.1 c, and this is 0.3 c. So this is this is more or less we expected. The expansion velocity obtained from this light curve and temperature fit is consistent with the subrelativistic ejecta with the more than 0.2 solar mass. And also this is a spectral feature. So this is a spectral taken by Gemini telescope at 4.5 days. So there are some broad feature in the spectrum, but we didn't see some clear signature of some emission line or absorption line. But there are some structures, which is consistent with the picture that the ejecta is expanding with the 0.1 c, and there are many atomic lines in this R process element. So, and now I a little bit talk about interpretation. So the Macronova or Kilonova is some thermal emission from the expanding ejecta, and which is heated up by the radioactivity. So initially, in the expanding ejecta, the density is too high and the photons cannot escape, even though there are significant amount of radioactive heat. So there, if I write some radioactive power as a function of time, radioactive heating is something like this. But we don't see photons escaping from this system. But when the system expands, at some point we will see escaping photon from ejecta. So initially it's dense, we don't see photons, but as it expands, at some point we start to see escaping photon from this expanding material. So photon luminosity should be like this, rising up to some point, and then afterward, after the peak, it should follow the radioactive heating. So this time scale is basically you can calculate this time scale, something like this. This is opacity of the R process element, and times the mass of the ejecta divided by velocity of the ejecta, and then its square root. And we expected opacity of the R process elements is quite high, so which can be 100 times high opacity compared to the supernovae. So we expected the peak time scale is 5 days, but actually what we see is peak time scale of half a day. So this tells you something like this. So opacity of the R process element is can be high and can be low. And what does it mean? So I'm not sure you don't know this lanthanide, which is some weird elements in the periodic table. So if you, and the lanthanide has a huge number of atomic lines around the optical wavelengths. So if your ejecta has a significant fraction of lanthanide, then you have a huge opacity, and then your peak time is quite late. So this is in the case that the ejecta has a fully lanthanoid, then your time scale is like this, week or so. But if your ejecta doesn't have much lanthanoid, then the opacity is low. In the end, you can have a faster rising time. And what we see is more or less consistent with this no-lanthanoid case. And this means this is composition of, this is solar abundance pattern of R process element. And here is lanthanoid. This is atomic mass number, and this is abundance pattern of R process elements. This is solar abundance, and lanthanoid is here. So probably this early rise light curve suggests that some significant fraction of the ejecta doesn't really contain the lanthanoid, so which may compose of the R process elements lighter than second peak. So this is one implication from the fast rise.
So is most of the energy generation taking place from the first peak, given the
It's a very good question. Yes, it's a very good question. If I use this abundance pattern, the most of the heat is coming from the first peak element. But in the first peak element, there are only few radioactive elements that can produce heat on the relevant time scale. So if there are only few elements, then the radioactive power is not really look like power law, but some exponential shape in the heating rate. But it's powered by these elements, and also the opacity is also dominated by this first peak element. Okay. So this is some R process calculation after the neutron star merger, and if your ejecta is neutron rich, you always have some quite neutron rich nuclei. So some process may avoid this kind of R process, but it probably R process finished somewhere around here in order to avoid to contamination of lanthanoid.
Well, can you be a bit more specific about the YE distribution and so on?
Yes, YE distribution is important. YE is electron fraction of the ejecta. If the electron fraction is low, which means neutron fraction is high, then you always have this kind of neutron-rich element. But if the electron fraction is high, which is, for example, 0.5, which is half neutron, half proton, in this case, our process doesn't occur in neutron star merger. So in that sense, YE should be like 0.3, between 0.3, 0.4 in order to stop our process around here to avoid the lanthanoid-rich ejecta. And initially neutron star has quite neutron-rich, but some neutrino process or some shock heating process can increase the electron fraction. So this is one implication. And this is a heating rate. I changed the composition. I used some solar abundance pattern of the our process element, and this is dependence of the heating rate on the composition. For example, if my ejecta is dominated by first peak, as I said, there is some feature of the heat. So it's not really look like power law, but there is some, on this time scale, some element dominates the heating rate. And if I change the composition from, for example, here to here, then what I get is something like this curve. So actually, there is some caveat. Heating rate depends on the composition by factor of few, so which means the mass estimate basically depends on the heating rate. So mass estimate should depend on the composition of the ejecta. So this is these points are light curves, absolute magnitude as function of time. So these are the detections. So here, this plot compare the kilonova which observed in this gravitational wave event and to the kilonova candidate which were observed after the short gamma ray burst. So there are few candidates after the short GRBs, but just only few points each short GRB. So for example, this short GLB had a candidate in infrared at this point, which is totally consistent with this event, and also this one. These three candidates, kilonova candidate after the short GRBs, really look like really consistent with the light curve which we observed this gravitational wave event. Okay, so this one is actually much brighter than what we saw in this event. So if these are really kilonova, so we think we already saw 4 kilonova in the history. Okay, now I want to move on to radio counterpart. So this is radio images. So this is a radio image taken on September 9th at 6 gigahertz. And this is an image on September 1st, which we don't see any signal here. But on September 9th, we see some radio signal here. And this is optical image. So the location is consistent with this optical image. And, but we see the radio signal much later than the optical timescale. And I want to show some nice animation made by NRAO, because I want to. So this is neutron star merger. This is some nice animation. Now to neutron star merge. and something ejected. And in the center, probably we have something accretion disk and jet is produced. But what I want to show you is not this, but following this. So after this ejection, what we expect is this. Oh. Sorry, I'm sorry. Let me do it again. So this is an animation for radio counterparts. So I want to show some specific feature of this. Yeah, so here we have jet. And now, in this ejecta, expand in interstellar space, and then this forms something like this. This is a shock wave propagate in an interstellar space. In this shock wave, we know this kind of shock wave exists also in a supernova, after the supernova, or many different relativistic explosions. And this shock wave in the interstellar space produces a radio signal. And this is a brief introduction of how the radio signal is generated. So suppose there is a blast wave propagated in ISM. Then this ISM, some electrons are accelerated in this shock wave, and also magnetic field is amplified in this shock wave. Then there is some accelerated electrons in magnetic field. We expect some synchrotron radiation. And this is one typical spectrum of the synchrotron radiation. Basically, there is some characteristic frequency here. And above this frequency, we see some power law decline. And below this, we expect nu to the 1/3. So there is some characteristic frequency, which is usually less than 1 gigahertz if the Lorentz factor of the outflow is about order unity. And this peak frequency is quite sensitive to the Lorentz factor, so it goes like gamma to the 4th. So which means if your outflow is highly high gamma, then this peak frequency can be much higher. So that's why we see X-rays and optical in the GRB afterglow, where we expect highly relativistic outflow. But if it's non-relativistic, we expect the radio is more bright than X-rays. So that's why for the mildly relativistic ejecta, the radio wavelength is kind of best way to see this blast wave. So this is what we see in radio. This is radio flux as a function of time. And here we didn't see any radio signals until about 2 weeks after the merger. And then we detected one here, and then now the radio flux is rising. So basically, and these different curves are the models from different energy, different setup. For example, these 3 curves are the models with the spherical outflow, with the mildly relativistic, which is Lorentz factor 1.5 or 2. And this one is off-axis GRB jet, so it's initially beamed, but after some expansion, it laterally expands, and at some point we see some signal from the off-axis jet. So basically, so far these models are consistent with the data, but you can see this flux approximately rises with the t to the 3, which is basically the radio flux is proportional to the volume of the shock ISM. And at some point we will see decline, because at some point this blast wave is decelerated, and then radio flux goes down. So in the future, we will see this decline. And the interesting thing is there is some implication from H1 observation of this specific galaxy, which is upper limit. But from this H1 upper limit, we can calculate what is the mean density, mean ISM density, which is less than 0.1 per cubic centimeter. So if this, if the ISM density is small, then in order to produce this flux, radio flux, we need the ejecta velocity should be higher than 0.7 C or something like this. And because this radio is still rising, so now what we want to do next is to measure the expansion size of this source. Because this event is so close, so the VLBA may be able to resolve this actual size of the ejecta. So this is angular diameter in microarcsecond unit. And this is expanding as a function of time. So if this is spherical relativistic ejecta with 0.2 C, this is goes up like this. But if it's a relativistic ejecta, we know the size goes like gamma times CT, which is called a superluminal motion. So above here, probably this ejecta can be resolved by VLBA. So we think if it's relativistic, we will be able to resolve the source soon. And this size should be different for the different model of the outflow. Okay. Now X-ray. So X-ray is also quite interesting because usually in short GRB, if we see X-ray, the X-ray is declining, initially very bright and then declines. But this time, what we see is very faint X-ray, which is more or less Eddington limit of this object is 9 times 10 to the 38 erg per second. And all the others are just upper limit in early time. So in order to consistent with these observations, on-axis afterglow is kind of impossible. If it's on-axis, it should be something like this. And if it's off-axis, for example, this specific parameter, you can see this. This is viewing angle of 20 degrees, and this is overpredict the X-ray flux. In this case, this viewing angle of 30 degrees is consistent with the X-ray data.
So is there's only one Chandra point. They didn't take or didn't try and get observations earlier?
There is actually, I would say, I think there is observation here.
Yes, an upper limit.
This is detection actually from different group. I think today there should be a paper that show the detection at here, but later people couldn't do it because there is some sun constraint. The location of the sun prevent you to see the X-ray. So unfortunately, we see. I think there are only two detections in X-rays. So it's really hard to say what produced X-ray emission, and probably it's off-axis, and probably spherical shock wave with the mildly relativistic ejecta also consistent with this data point and the upper limits. And one thing which is interesting is actually, I didn't explain, but there is parameter here which is called P. P is the spectral shape of the accelerated electron. So if you write something like D and D E, E is energy of the electrons, which goes like energy to the minus P. So this is power law index of the electron, accelerated electrons. And the higher frequency spectrum depends on this P. And if you want to say the synchrotron radiation produce both radio and X-ray at this time, on this time scale, you can get what value of P is consistent with the X-ray and the radio. So, and this implies P is about 2. And this 2 is kind of very small, actually. If you plot the P distribution of the previous short GRB afterglows, then P is usually larger than 2. So it's kind of small end of the previous observations. So
isn't this what you'd expect from
theory?
classical Newtonian diffuse shock acceleration models?
Yes, yes. Yeah, but recent simulations suggest like P is 2 point something.
So you say you think it's consistent with 2.2?
Yeah.
Because there's enough dynamic range
Yeah.
and frequency that you can tell small differences in spectrum. But there could be some additional contribution to the X-rays besides the shock electrons, right?
Right. So yeah, I think there are still there should be different explanation rather than synchrotron radiation from the shock, because it's not really huge. I mean, compared to the optical, we get peak luminosity of 10 to the 42. Compared to the optical luminosity, X-ray is quite small. Okay. And we can't see this source until November. Yeah, before going to gamma rays, I want to say, yeah, this is jet. Probably you know the concept of the beaming of the jet. So if you have jet with a high Lorentz factor, so there should be some relativistic beaming. And if you are off axis, then you won't see any signal. Not any signal, but a very, very faint signal compared to the on-axis observer. But as time goes, the jet slows down, and this process expands jet. So jet half opening angle increases, and also Lorentz factor decreases. Then this relativistic beaming becomes weaker. So even though you're off axis at first time, at early times, but you will be in this emission region at later times. So this is why this off axis light curve rising up at some point. This is a time scale when you start to see the jet. And this is important concept, and especially to interpret what is this gamma ray burst that we see just after the merger. So this is a gamma ray flux observed of Fermi GBM, and this is integral. This is time scale after the merger. This delay is more or less 2 seconds, and duration also more or less 2 seconds. If you look at just this light curve, this is quite similar to normal short GRBs. But what is special, this is mentioned also in this morning press release. If you take into account this distance is quite close, then the gamma ray isotropic energy is just 5 times 10 to the 46, which is 2 or 3 orders of magnitude lower than the weakest short GRB we ever seen. And the peak of the spectrum is of this initial pulses like this 200 kV. And also it's interesting, this spectral shape changes from this harder spectrum to softer spectrum with time. Yeah, so duration is similar, but much fainter than the short GRB that we know. So there are a few, actually this is puzzling, but this just look at these three features, we can say something about the nature of this, origin of this gamma ray burst. So this is famous argument of compactness problem of the gamma ray burst, because we see huge amount of gamma ray photons in few seconds, which means you have very intense radiation field in the emission site. And if we just assume non-relativistic outflow, it is impossible to escape such gamma rays without creating pair electron-positron pairs.
But you're not seeing gamma rays above 511, are you?
No, we
So
don't see.
That's not a constraint.
Yes, but right. But the spectral shape suggests some power law plus exponential cutoff. Then even this exponential cutoff,
Okay.
yeah.
But then you don't necessarily need much of a Lorentz factor to put the highest energy gamma rays below 511 in the rest frame.
Yeah. So yes, that's why we get somewhat weak constraint on this Lorentz factor. So if you put the gamma ray spectrum like power law plus exponential and the peak energy of this energy, then you can get still some limit on the Lorentz factor of 2.5. So this suggests that the outflow which emits gamma rays must be at least mildly relativistic. So this is one argument we can make. So, and there are possible explanations of the origin of the gamma rays. So one is on-axis but very weak jet. And second one is we see gamma rays, but we are off-axis, but quite slightly. If we are very close to the edge of the jet, then you will see some faint signal. So this is another scenario. And third one is kind of shock breakout, because you have a jet. If your jet is delayed, like because we see gamma rays after few seconds after the merger, so it's likely the jet drilled the ejecta. So during this interaction, there is some shock, and this shock breakout may also produce gamma rays. And basically, this on-axis very weak jet can be ruled out because we didn't see X-ray afterglow at early times, but late time, which is inconsistent with this on-axis picture. And also, slightly off-axis jet is also predict early X-ray and radio emission. So I think we consider this shock breakout produces a small amount of mildly relativistic ejecta can produce shock breakout gamma rays. So, but please see this in details. So now I want to really discuss the implication of the RPOS element in the galaxy. So this is a phase space of this galactic merger rate as a function of the ejecta, the amount of RPOS elements ejected by one astrophysical event. So in order to explain the total amount of RPOS elements in the galaxy, you want to be on this region. So this is given total mass of the RPOS element in a galaxy, we can calculate what is the rate and the ejecta mass per event. So this is kind of something like this. If you want to say the supernova, each supernova produces RPOS elements, and we know more or less the rate of the supernova in a galaxy, which is somewhere here. So the supernova, it is enough that for the supernova scenario, each supernova produces something very small amount of RPOS element. But we know compact binary merger, the rate is expected around here. so like 10 mergers per million years. In order to explain the total amount of outflows elements in a galaxy, the mass ejection should be somewhere here. And also there are other constraints from different observations, like there is some geological plutonium measurement, abundance of the plutonium in on Earth's sea. And this is the outflows abundance in dwarf galaxies. So we expect this, the mass ejection, amount of mass ejection and the rate should be around here. And now I can put the implication from this event is somewhere here. So it's the rate sounds a little bit high, but still, which is consistent to explain all the outflows elements in the Milky Way.
If you incorporate the lower electron fraction that we saw in this event, does that change the implications of this plot? For
Yes.
example,
Yes.
So how does that fold into this?
Yes, I didn't explain. Yes, this is one complication of this plotting this figure. So here I put A is larger than 90, so which means I assume each neutron star merger produce elements above 90, so which means above here. So in that figure, I assume that neutron star mergers don't produce fast peak elements. But the mass in the fast peak element is huge. So if you change the assumption, the neutron star merger produces all the outflows elements, including fast peak, then everything should shift to, so this shift this way. So every neutron star merger has to produce more outflows element. But actually this range I basically take into account the uncertainties in the, so because I told you the minimal amount of mass should be above 0.02, but I extend to this. This is because of the uncertainties in the minimal electron fraction, basically. What time is it?
You have another couple of minutes.
Yes, I think this is the EM counterpart, so I think I should stop here. And if you have questions, please.
So we have time for a few questions.
So, Kenta, can you come back to the scenario, the shock breakout scenario? Does this satisfy the closure relation from, in the CAF 20?
Yes, you can find.
Does satisfy the closure relation?
Yeah, you can find the parameters satisfy. So now, actually, I and Udi and Suvi and me working on this finding closure the parameters which satisfying the closure relation. And
What again is this closure relation?
There's a relation between the maximum energy, the time of the burst, and the total energy that you get from shock breakout, and they all have to satisfy certain equation quality. It's in the paper from 2012.
So this is radiated emission from the breakout of a shock across the surface.
Yeah.
yeah, so in this case, it's a little bit different because this is not stellar surface,
Yeah.
but what you have is ejecta surface.
It's not clear exactly how smooth.
Yes, yeah,
the
exactly.
surface is.
Yeah, so it's a kind of what we still don't know. But
Do you have another question?
Well, I was just wondering if there was any millimeter wave active glow measurements
millimeter wave.
in between optical and radio.
There is.
In on modeling.
You mean modeling? Or?
Well, it would help with the synchrotron absorption
Yeah.
modeling and so on.
Oh yeah, yeah,
Shock
yeah,
modeling.
sure. There are upper limits by ALMA,
I see.
but no detections.
Can you comment a little bit more on point 2 here? So a lot of the other aspects of what you talked about make this appear very consistent with just being slightly off axis
Mhm.
for the jet. If you modify the gamma ray burst model so that it's maybe not like a top half, it has some kind of
Yeah.
fall off, can you make that a reasonable model, or do the gamma rays make it hard to be off axis?
Yes, you can explain gamma rays. Then you will have a trouble. Actually, these constraints are basically coming from X-ray upper limits and also
This
radio
made
upper
it seem
limits.
like a 30-degree opening angle is perfectly consistent. But is the problem then that you can't get the gamma ray burst to work at all?
Right. If you're this case, you have to be. I think this jet is assumed to be half opening angle of 10 degree or something. If you are 30 degree from this 10 degree jet, then
And that's a steep fall.
steep, very, very steeply decay.
One of the big uncertainties of this whole business is how much structuring there is of the jet.
Right.
What the energy flux distribution about the core of the jet is. Is it sharply cut off, or is there a tail? And, you know, nobody knows.
But yeah, I think that still it's hard to satisfy these constraints on the off-axis prompt emission. It's I don't know. I think it's very hard.
So I don't know much about this. The fact that you see this source so far outside the optical disk of the galaxy is that when you show the optical image
Mm-hmm.
of S0 galaxy, this source is very quite far out.
Yes.
Is that consistent with the expectation that you see from massive star, jetstars, and
Yeah. This is a. This is 2 kiloparsec away from the center.
oh, I see.
It's not.
That's
Yeah.
large.
Yeah.
Oh, okay. That's not the entire galaxy.
So I will take this
Mhm.
opportunity to jump in and make a shameless plug for tomorrow afternoon. So at 2 o'clock tomorrow here, me and the other members of the CITA Light Group will discuss the gravitational wave side of this discovery in a bit more detail. And there is a paper that's available today, accepted in Nature letters, that discusses the implications of a binary coming from this galaxy and appearing at this distance away from the center, and constraining it and stuff, and other things. Back to Kenta. More questions?
Thank you. Yes.
The afterglows of some gamma ray bursts, radio afterglows, have been observed and were shown to fluctuate in amplitude on a short time scale. Were there
Right.
any follow-up observations of the radio detections? How often were they done, or was it just one brief measurement of the flux density, or were there several measurements?
Yes. There are a few, actually. There are so far. Actually,
Those are all of the measurements.
yeah.
Yeah.
There are many actually that.
We are only like this far away from the
Yeah.
discovery.
Actually, there are many observations but this figure just plot 4 detections, and yeah, probably, yeah, you will see some scintillation.
That's my
Yeah.
question is whether any scintillation has been detected in that signal. Because for gamma ray bursts, the afterglows, was used to put a constraint on the angular diameter of the
Yeah.
afterglow.
Right. Yeah. Probably this early time. Yeah. But afterward, I mean, on this time scale, is probably the angular
Pretty large.
diameter, yeah, too large to. Yeah.
May I ask a question for both of you?
Yes.
is the mass measurements from the vibratory signal consistent for reasonable equation of state with a long-lived, rapidly rotating neutron star remnant? Or does it more or less require a direct class of the black hole?
I think we can,
The total mass is 2.7, so I think that there are going to be equations of state that make that a long-lived remnant. There are also constraints on the tidal deformability.
But it's 2.7 plus or minus.
Plus or minus some, yeah. And so, and there are also constraints on tidal deformability. So we were just discussing before this talk whether what can be done and had been done to combine those into the answer to the question you just asked, but we didn't have an answer right away. But total mass 2.7, that's fine. The question is, do the extra tidal constraint, tidal deformation constraints we have further sharpen that kind of down? So we'll have to get back to that.
Cool. So if there are more questions, think of those questions. Because I want to, so this plot effectively mean that you, in the next month and a bit, will be able to pick one of these.
Mm-hmm. Yeah. Yes. That. Yeah. Yes, exactly. That is that will occur. Yeah. Yeah, and back to your question. So it's related to your previous question about the electron fraction. In order to get the peak time scale of less than 1 day, we want a high electron fraction. But it's very difficult to get high YE ejecta with just direct collapse to the black hole. So to get this high YE ejecta, we want to have a massive neutron star at the center, because this neutron star can emit neutrinos, and neutrinos interact with the ejecta, and then electron fraction can be higher. So this is one thing we speculate there is at least some short-lived massive neutron star after the merger. But we don't know really the direct collapse to the black hole is really ruled out or not. It's still, we don't know, but it's kind of speculation.
We probably have time for another last question. If it's the last question. Yep.
What are the cosmological implications of the lens? Because it was said earlier that one forgets optics with the potential waves at the same time that the wave is transformative.
Yes.
Discuss that.
I think
Yeah.
you
So
should.
yeah, the association between the host galaxy and its galaxy group gives us a redshift or recessional velocity of this source. And then from gravitational waves, you have the direct measurement of the luminosity distance. So from that, we have then turned that into a measure of H0. It's a very broad agreement with all previous things. It's 70 plus minus 10-ish.
That's not terrible. It's just covers all.
Yeah, no, it's
standards, right?
it's great because it's completely independent of everything that's ever been done before, which is great.
Right. If you get 10 more, then we...
Yes, I don't remember exactly how many you need.
This event was exceptionally close, which meant that the distance uncertainty was pretty small. So you would expect that more of these will tend to come with larger distance uncertainties. So even if we localize them, you can't just do a square root n. But yeah, with a sufficient number, maybe 10 to 100, then yeah, you would constrain down to a similar level to other sources.
Yes, and with that, I think we should thank Kenta again.